Started today, and as we get started, I just want to remind you that today's online lecture was the last lecture in Chapter 2. We're starting Chapter 3 on Friday. So that means that we will be really working on our appendices. I don't know how the exams are going to look. The numbers I have of students that are not eligible to come to class due to being in quarantine, I don't know how we're going to run the exams. But whatever the case may be, if we all do it all online or we do some of it in person, having a physical copy of these things is necessary to get your exam done in 2 hours. If you're trying to search on a web page on the screen, it's going to suck. So please get it printed out. You don't definitely need it on Friday, but I would highly encourage it to start working on Friday, because that's when that's when we have to start really working on that part that I think that the material starts to get a little bit more challenging. So please understand that. So that's my announcement that's starting this morning. Today we're going to go over heat transfer. Now again, as we talked about in the lecture, this is one lecture that is an entire class in mechanical engineering curriculum. So let's talk about the 3 types of heat transfer that there are. These equations are all on your equation sheet, but you should know that conduction, it happens in solids, and the equation is minus Ka times dt over dx. Okay, we can write dt over dx as T2 minus T1 all over x2 minus x1. You can recognize that K is something called a thermal conductivity. You need to know this in case I give you thermal conductivity. I don't say K is equal to, I say the thermal conductivity is equal to. You need to know what this is. So if I go to my table A19, E or otherwise, is going to be the table of all the substances, and it's going to have the thermal conductivity here listed down in this chart. Okay, that's provided for you. You can look this up. It's a property of the material. It doesn't change. Okay, so we need to know that. We need to know where they are. I think a test last year I just didn't give them any symbols. I just said things in words, and that screwed with people's minds. They said, I know how to do it if you give me the symbols, Dr. Wanklin, but I don't know it if you give me the words. And they said, that's unfair. And I said, when you start talking to me in symbols in our conversation, then I will start giving you questions in symbols, because that's not how we talk. I mean, unless you're weird. And then you don't have any friends, and then you're probably in your basement right now. Hi. So anyway. The next one, Q dot convection. Okay, that's going to be H times A times, let's just say here, T2 minus T1. We can determine which temperature we're working with there. If there's a base or the solid or the fluid, this is a convection that goes between a solid surface and the air or liquid around it. This H is called the heat transfer coefficient. Okay, my brain just shut off there for a moment. Heat transfer coefficient. All right, now these areas that I'm dealing with here are actually surface areas. So again, you need to know the surface area of a circle, of a cylinder, of a sphere. You need to know those things. They're not on your equation sheet. Please know how to do those things. In these 2 equations, the delta T, it doesn't matter if I'm dealing with Kelvin or if I'm dealing with Celsius. Those are the same step size. Doesn't matter. Doesn't matter if I'm dealing with Rankine or Fahrenheit. It doesn't matter, because the delta T is the same for both of those. All right? But we are going to change down here when we have Q dot radiation. It is going to be epsilon, which is going to be the emissivity, a number between 0 and 1. How do you know if you're going to use that equation if we neglect radiation or include radiation? Does the problem statement give me emissivity? You can't look that up. It has to be given to you. Okay? Sigma is the Stefan Boltzmann constant. It's given to you on your equation sheet. Area, it's the surface area once again. And then this is going to have, I'll say T2 to the fourth minus T1 to the fourth. Now I'm not putting this as surface and surroundings. I'm just calling them T2 and T1. Just trying to change things up a little bit so you're not stuck to some nomenclature. But here, because we raise the temperatures to the fourth power, we must put things in absolute temperatures. Okay, must be an absolute. If you forget, if you're uncomfortable, if you this drives you nuts, put everything in all our temperatures into absolute temperatures. You're going to be okay. You're going to be okay. Okay, that is the fail-safe. But it could save you some time if you recognize conduction and convection doesn't need to, because I'm going to give you temperatures in Celsius and Fahrenheit on these exams. I'm going to try to get away from giving you temperatures in Kelvin and Rankine, because you don't go, the bank clock doesn't say the temperature in Rankine outside. It says it in Fahrenheit. So that's what I'm going to give it to you in. Okay? Yeah, when I say absolute temperatures, I mean Rankine, because we're starting from an absolute 0 and raising up. So those are absolute temperature scales. Just like an absolute pressure scale is measuring from 0 up. And then there's a gauge pressure, which is a pressure gauge, but we're always going to deal with absolute, where 0 is nothing, a vacuum, absolute 0. That's what we're going to deal with in thermo. Now, in the equations that we've been talking about in this class, we have developed the first law of thermodynamics. Remember, delta KE plus delta PE plus delta U is equal to Q minus W. Notice this is Q. This is heat transfer. And the three equations I gave you were heat transfer rate. I can't put any of these equations, these things I calculate, into this first law equation unless I say that Q is equal to the integral from 1 to 2 of the heat transfer rate over time. Take it times the time. I mean, we get measuring these in kilowatts, which is it's kilojoules per second. Then I have to say how many seconds it's acting to figure out what my heat transfer is, Q. Or what I can do is I can rewrite this equation as delta E is equal to Q minus W. Why am I saying delta E? I'm just saying the change in all the energy, the internal energy, the kinetic energy, the potential energy. I'm getting really tired of writing it all that, so I put it all into one delta E, all the properties, the change in all the energy. Okay, now, what I can do with this equation is I say, well, let's see what I can do if I put this on a time basis. So I'm going to divide by dt, and I can get here dE dt is equal to Q dot minus W dot. Now I have the first law into a rate form. The change in energy with respect to time is equal to the rate of heat transfer minus the rate of work. The rate of work has a special name. It's called power. Okay, that is a 10-minute review of what I think you need to know for this material. If we were doing this online, I would break and then I'd ask you a question. But we're here in person, so let's go ahead and let's do a problem that works with this. Okay, so here's our problem, our example. I have a gearbox. And you don't need to know what a gearbox does. If you're a mechanical engineer, you probably should be working that way. But a gearbox here, we're going to just basically say it has 2 gears, and I'm drawing a cross-sectional view of this. And these are looks like they're solid cylinders, but you know, gears are going to be meshing together, and there's going to be 2 shafts here coming in and out of this box. And one shaft is going to rotate this way, and one shaft is going to rotate this way as those gears mesh together. And the gears are going to be different sizes, and it has different, makes different velocities on the shafts. different angular velocities. But we're not going to get into that. That's a whole different class. We just know that we have a gearbox here. And I want, excuse me, I want to say that this gearbox is running at steady state. So we have to think, oh no, that word steady state's coming up here. Well, that means that this gearbox, we're not just starting it up. It's been running for a while. It's running steadily. It's running constantly. That's what I'm analyzing at steady state. And I want to do that almost every thermal question I work with. Okay. And it's saying that it receives 60 kilowatts through the input shaft. So this is my input shaft, and I'm going to say this is 60 kilowatts of power, because kilowatts, we're dealing with power, rate of work, are coming into that first gear. Okay. And it's going to be delivering power out from this second gear, but we don't know what power is coming out there right now. It says here that the gearbox as a system, okay, so that means we're going to be looking at this gearbox, this yellow line. This is going to be my system that I'm going to be analyzing. The gearbox as a system transfers energy away from its surface by convection. So we have Q dot convection that is coming off of this surface. And they told us the heat transfer coefficient, H, is equal to 0.171 kilowatts per meter squared Kelvin. They told us that the surface area is equal to 1 meter squared. So this gearbox has a meter squared of surface area. And its temperature of its surface is 27 degrees Celsius. And the temperature of the surroundings is equal to 20 degrees Celsius. So we know a lot of information here. We're running this at steady state. We have convection coming off here. We're going to say that the heat transfer coefficient is 0.0171. We know it's 1 meter squared on the outside of it. We know the temperature of the surface. We know the temperature of the surroundings. We know there's a delta T. Heat is going to be moving. The mode of heat moving is going to be convection. The first question is, what is the heat transfer rate? What is the heat transfer rate? Okay, that's a word. What is heat transfer rate looking for? It's looking for Q dot. Q dot is heat transfer rate. So I look at my equation sheet and think through myself, I'm dealing with convection only, so that's just going to be Q dot is equal to HA times T of the gearbox minus T of the air around it. Again, I'm just labeling these as different letters here so we're not getting stuck with what I'm talking about. I'm going to put the high temperature minus the low temperature. Okay, now I just plug in. What is my heat transfer coefficient? 0.171 kilowatts per meter squared Kelvin. My area, 1 meter squared. My temperature of my gearbox is 27. My temperature of my air is 20. And I'm going to go ahead and say that difference is in Kelvin. Even though the temperatures are in Celsius, the delta T, 7 degrees, is going to be the same in Celsius and in Kelvin. So I'm going to put it in Kelvin here because that helps me with my units. Okay? But understand that delta T in Celsius is the same as delta T in Kelvin. I keep saying this over and over and over again. Just try to make sure we understand that. And now I'm going to check my units here. Meter squares goes away, kelvins go away, and I have kilowatts as my answer, and kilowatts should be my answer because that is a heat transfer rate. Okay? And now I got to pull out my trusty calculator, and I got to type all these things into it and make sure, see what we have. So we're going to have 7 times basically 0.171. Okay, so I get here that the heat transfer is going to be 1.197 kilowatts. That is the answer to part A. Okay, what's the heat transfer rate? Plugging and chugging. The algebra is not hard. Sometimes it's the negotiation between the problem statement about what I put in here that's the hard part. Part B, what they want to know is what power is developed with the output shaft? Okay? So what we're looking for is this power. Well, I'm looking at that, I have to look at my system, and I have to write a first law equation for that system, but I'm going to write it in this form. I'm going to say that dE dt is equal to Q dot minus W dot. Okay, that's my first law. I've put it on a rate form because everything in this question is a rate. I've calculated heat transfer rate, and I found rate of work. I want to find rate of work. Now, this problem is saying steady state. It's saying the properties are not changing with time. So it's telling me the property of energy is not changing with time. So I know that this term here goes to 0. The energy is not changing with time. It's steady. It's not going up. It's not going down. So my equation here, my first law equation that I've modified and put into a rate form, is now just going to say that the heat transfer is going to equal the work for my system. So maybe I should put the summation of all my heat transfer and the summation of all my work. Okay, what should I put down here for Q dot? What is my Q dot? What is my left-hand side of the equation going to be? What should I write down on my tablet? What we found in A. So I'm going to put 1.197 kilowatts. Is that correct? Let's do fist to 5. Have I talked about fist to 5? 5 means yes, completely correct. Fist means no, that is incorrect. You put yourself in there, but somewhere in between means I don't really know. Okay? Fist to 5. Correct or incorrect? There's a lot of... Okay. The answers should be fist. It's incorrect. What? Okay, it is a rate. Kilowatts is a rate. It's good. We're asking good questions. It's a rate. It has to be negative. Okay, we say, oh, but Wanklyn, I got the right number. Yeah, you did. You got the right number. But until we get the right sign, the problem is wrong. Okay? This heat is leaving our system. So even though we calculated it that above was positive, that was the magnitude. It's leaving our system, so we have to put a negative sign here. Okay? So you can argue, yeah, you know, it was right. I think it was right, but it was technically wrong. Okay? Now the work. Well, we know there's two works here. There is a shaft coming in rotating, and that's causing a shaft going out. Okay, so I know that the shaft coming in is 60 kilowatts. Is that what I put there? It's negative because that work is coming in. What work is coming out is going to be this work out is what I'm trying to find. Okay, now if I work with this, if I calculate this, which is a pretty easy calculation, 60 minus 1.60 minus 1.197, we get that the work out is equal to 58.80 kilowatts. Okay? The math is easy. You look at this at a solution, you're thinking, man, I can do that. That's simple 4th grade math. I know that because I'm teaching 4th grade at home when I'm not at here. Because my son's taking 4th grade. And that sucks too. 4th grade over Zoom with a whole bunch of people saying mute your mic. That is my own personal hell. 1st grade, they got it figured out. They're just drawing pictures of family all day. That's just beautiful. It's easy to draw me. I'm a bald guy with a beard. I look the same, but I have pokies. My daughter makes sure I have pokey hair, so it's wonderful. Good. You don't care, but I care about that. All right. So it's the signs that really cause you issues here. Make sure you get the signs. And I'm not going to try to trick you on, I'm going to tell you clearly what's happening. You have to negotiate with the problem statement and tell what's going on here. Now, the other things they said here is that what happens if we considered radiation? If we considered radiation and we said that the emissivity is 0.8, how much radiative heat transfer are we going to have with this? Okay, so I would write my equation. Q dot radiation is equal to epsilon area sigma times T here is going to be T of the gearbox to the fourth minus T of the surroundings to the fourth. And I'm going to just plug things in. 0.8, it doesn't have any units, it's unitless. The area is 1 meter squared. Sigma is my favorite constant. 5.67 times 10 to the minus 8th. Easy to remember in my mind. 5, 6, 7, 8. Negative 8 here. And this is going to be kilowatts per meter squared Kelvin to the fourth. And then I'm going to put in my temperature of my gearbox, which was 27 degrees Celsius. I know I have to put it in absolute, which is going to be 300 to the fourth. The temperature of the surroundings, I have to put in degrees Kelvin, which is 293 to the fourth, and this is going to be Kelvin to the fourth. And again, our units are going to cancel out and give ourselves kilowatts is what we need. Now, I encourage you, if you do this number here, 300 to the fourth, 300 to the fourth, minus 293 to the fourth, you get a big number here, 729949199. If you do 27 to the fourth minus 20 to the fourth, you get a smaller number, 371441. That's a huge difference. Okay, that's why it doesn't work. Some students will do this number here at the top, 37121441, and then add 273 to that to convert it to Kelvin. That's still way far off. No, this is why we have to do absolute here. Okay, now if we do this calculation, plug it into the calculator, Q dot is going to be equal to, this isn't in kilowatts, this is actually watts per, this is actually watts. Make sure you get that, that's actually watts. I messed that up. That's watts, and so you're going to get 3.11 watts or 0.03311 kilowatts. Okay, it's a small kilowatt. It's not even a kilowatt. It's 0.03. Now the problem statement might say, if there is that radiation, you know, we should have to go back up here to this first part and say the heat transfer leaving it is not just 1.197, it's 1.197 plus 0.03. Okay, which puts me at, 1.20. Is that enough for me to worry about? We're going to neglect it. Okay, if we did, we could recalculate part A here and then recalculate part B, but our numbers wouldn't change very much, so that's why we often neglect radiation. It's a small value. Any questions on this problem? Okay, I'm getting a lot of questions about a problem on your homework. I'm going to do a similar problem for that. We're going to be talking about heat transfer through surfaces. Okay, walls. I think on your homework you have a brick wall and a steel plate on that wall, and you're looking at the heat transfer through that. Heat transfer rate, steady state heat transfer rate. Steady state heat transfer rate. When it goes into a system, it comes out of a system. It's steady, doesn't change. Q dot in is equal to Q dot out. So when we're dealing with these composite walls, these multiple things on a wall, we are going to say that this Q dot is constant, which means if there's air over here and air over here, this means that Q dot convection, which is outside, Q dot convection is equal to Q dot conduction, which is equal to the Q dot conduction, which is equal to the Q dot convection. Okay? Every Q dot is the same in every individual piece of this. It's like current going through a circuit, which is a way we can analyze this, which I'll hopefully have time to talk about at the very end of this class. Okay? Now, if there was radiation that we had here going in, we would have Q dot radiation plus Q dot convection is equal to Q dot conduction, which is equal to Q dot conduction, which is equal to Q dot radiation plus Q dot convection. Okay, because those two things, the radiation and convection added together, would have to equal that conduction. What comes in goes out. And that's the whole principle of the homework problem that you have when you're dealing with the wall. Okay, so our walls can be very complicated. And then when we take heat transfer, you'll deal with complicated walls. But we're dealing with pretty simple walls. And so the problem that I'm going to do here is a pretty simple wall. It has two layers of this wall. The first layer is insulation. And they tell me that the K value of this insulation is going to be 0.029 BTUs per hour per foot per degree Rankine. And they tell me that we're dealing with 3 inches of this insulation. 3 inches of insulation. And then out here we're going to have siding. And the K value for the siding is equal to 0.058 BTUs per hour per foot per degree Rankine. And the siding is not as thick. The siding is 0.75 inches, 3/4 of an inch. Okay? They tell us that inside of here, if we measure the inside of the insulation, the temperature is equal to 67 degrees Fahrenheit. And they tell us outside the temperature is -8 degrees Fahrenheit. It's a cold sucker outside. And they want us to know, what is this temperature in the middle? Okay, so this is a massively simplified problem because you're not going to have a wall like this. You're going to have drywall, and then you're going to have insulation, and then you're going to have something outside, and you're going to have maybe a foam that's put outside of that. Then you're going to have siding on top of that foam. So that's complicated. Okay, but this is a much simpler wall, and so that's what kind of we're dealing with. So what we need to say here is that the facts that we know, the Q dot, the heat transfer rate in the insulation is equal to the heat transfer rate in the siding. That's what we know. Okay, so let's set up the equation here. It's going to be minus K of insulation times my area of my insulation times T2 minus T1 all over X2 minus X1. And that's going to equal minus the K of my siding times the area of my siding times T2 minus T1 all over X2 minus X1. Okay, now I use T2 and T1 just willy-nilly there. We're going to have to define what T2 and T1 is for the insulation and what T2 and T1 is for the siding. Okay, I need to make sure I get that right because they're not the same T2 and T1. But the first thing I can do is say, look, if this is equal to, this negative sign cancels out. Don't have to worry about the negative sign. Both have a negative sign, get rid of it. Divide through by -1 if I want to do it that way. The second thing I look at is the area. When I'm looking at this thing from the side, I'm going to look at an area of the insulation, and that's going to be the same area of the siding. Okay? I'm just looking at something. It isn't like there's a smaller siding area than there's an area of insulation. So I can cancel out the area of the areas. They're the same areas. When would this not be the same area? Well, we know that wall over there has studs in it, right? There's going to be studs 16 inches apart. And so there's a possibility that if you were looking at how the heat actually transferred for the wall, that there is going to be a big area of drywall, and it has a choice. Am I going to go through the insulation or am I going to go through the stud? And there's different areas that it can go through there. This is an easier problem. You don't have to worry about that. Okay? So if I were now to plug in numbers here, I'm going to get 0.029 BTUs per hour per foot per degree Rankine. Then I'm going to say T2 for my insulation. T2 is my unknown temperature T. T1 is my known temperature 67 degrees Fahrenheit. Okay, I'm going to put this, the difference here is in degree Rankine, so I'm going to put that here in degree Rankine to cancel us off because the delta F is equal to the delta R. Step size is the same. X2 minus X1. Well, X2 is going to be 3 inches. X1 is going to be 0 inches, I'm going to just say. X2 minus X1 is just how thick was that going through? It's going through 3 inches. Okay, this is going to be in inches. That's going to equal 0.058 BTUs per hour per foot per degree Rankine. Okay, now, in this T2, now we're only looking at the siding. So the T2 for the siding is minus 8. The T1 for the siding is our unknown T. This is in degree Rankine. And our thickness here is going to be 0.75 minus 0 inches. Is everybody okay with that? I could have called this T1, T2, and T3 if I wanted to. I didn't. I called them, I just wanted to look at the insulation, T1 and T2, the siding, T1 and T2. Okay, now, if I look here, this is one equation with only one unknown. And that one unknown is the temperature unknown. It's this. This is the only unknown here. Same temperature. Okay, so we have, if we calculate this out, now look here. I don't have to do any conversion if I don't want to do any conversion because I keep everything in the same units. BTU hour, foot, degree Rankine, BTU hour, foot, degree Rankine. I have inches and inches. I have Rankine, I have Rankine. I know my units are all going to work out. They're all going to work out. I might want to convert this from inches to feet because usually I don't want to mix feet and inches together. So I would divide this by 12 and I divide this by 12 and I would then have feet. But I hope you understand you don't have to. You don't have to. Okay? So if we solve this, it's just a bunch of algebra. Okay, we solve this. I'm going to divide through here by 0.058. So 0.029 divided by 0.058. I'm not going to worry about units because it's okay. 0.5 times t minus 67. 3 divided by 12 is 0.025, of course. Then we're going to have negative 8 minus t all over 0.75 divided by 12, which is 0.0625. Okay, what's 0.5 divided by 0.25? Well, that's 2. 2t minus 67 times 2, 134. I rely too much on my calculator. I probably shouldn't. Minus 8 divided by 0.0625. This is going to be minus 128. Minus 1 divided by 0.0625. 16t. This is not the only way to solve it, of course. You can solve it many different ways. I'm going to have 18t is equal to 134 minus 128, 6. My temperature is going to be 6/18, which is equal to 0.3333. What's my units on that temperature? I didn't keep them here, but what's my units on that temperature? Is it Rankine or is it Fahrenheit? It's Fahrenheit. because I didn't change this temperature up here to Rankine. Okay, it's in Fahrenheit. Okay, it's in Fahrenheit, so this is degrees Fahrenheit. Now I'm going to ask myself the question, does that make sense? And I go look back up here, and I'm saying this temperature is 0.333 degrees Fahrenheit. Okay, that makes sense because I had to have heat. It's 67 degrees Fahrenheit to about 0 makes sense, and then 0 to -8, that makes sense. If I found that interfacial temperature to be 72, that's incorrect. I couldn't have heat transfer that direction. If I found that interfacial temperature to be -10, that couldn't be correct because I couldn't have heat transfer in that direction. It has to be between those two numbers, and it looks like it's skewed towards the outside temperature. That makes sense. Okay, we're always going to look at that. Okay, now, there is another way to do these problems, and it's called the thermal resistance method. So I'm going to, first of all, are there any questions here about this? If I wanted to now I could solve for what Q dot is per unit area. I could just find out, I could plug my numbers in here and find out how many kilowatts per meter squared of heat transfer I have. Okay, the other way we can do this problem, it's provided in your book. I usually don't get enough time to talk about it, but it is a way to solve complicated questions. In fact, when you take heat transfer, if you do take heat transfer, the way we will analyze these are with thermal resistances. So thermal resistances. Okay, we know that voltage is equal to current times resistance. Okay, if you're a mechanical engineer, often you don't, when you see circuits, you kind of seize up a little bit. But we know this, V equals IR. We are going to say current is equal to V over R. Okay? And we're going to make an analogy to thermo. We're going to say that the heat transfer rate is going to be equal to our current. We're going to say that T1 minus T2 is going to be equal to our voltage. That's what's driving things, is the temperature difference is what's driving things, just like voltage drives things. And then we're going to have a thermal resistance. Which is equal to our thermal. Okay, so how does this work? Well, let's look at our conduction equation. Our conduction equation is equal to Q dot is equal to minus Ka times T2 minus T1 all over X2 minus X1, sorry. Well, I am going to switch the order of my temperatures, and I get this. Ka T1 minus T2 all over X2 minus X1. In changing the order of my temperatures, I got a negative sign that appeared, and I just got rid of the negative sign here. So basically, I multiplied through by negative, and that flipped the order of these temperatures. So, what I'm going to do here is I'm going to call this X2 minus X1, I'm going to call this just my length. And so I can rewrite this as Q dot is equal to T1 minus T2 all over length over Ka. I'm taking advantage of, if I divide through by this, it's a way of bringing this into the denominator. And now what I do is I have this sucker right here is my thermal resistance. Okay, let's look at convection. This is conduction. In convection, I have HA times T1 minus T2. I can rewrite this as T1 minus T2 all over 1 over HA. This is my thermal resistance. Going through this quickly. However, now if I'm looking at a problem and I have air, I have insulation, I have siding, I have air, I can draw this as a series of circuits. resistances, where this air has a resistance of 1 over HA, whichever is H1A. This is going to have a thermal resistance of L over K insulation A. This is the length of the insulation. This is going to have a resistance of L, the length of the siding, over K of the siding times A. And this resistance is going to have 1 over H2 times A. And we have our current running through this is Q dot. And we have nodes. We know that this is going to be 68 degrees Fahrenheit, and this is going to have temperature of minus 8 degrees Fahrenheit, 67. And now we just can find out by adding up resistors in series, we can now do these calculations the same way. And it's simpler in many cases. And when you're dealing with complicated paths, like remember that path I was talking to you about before, now if the wall has two choices, it can go through the insulation or it can go through the stud. Those are parallel resistors, and we know how to add up parallel resistors. We know how to add up resistors in parallel and resistors in series. So this is a way that you can solve problems. And if you want to solve problems like that on your homework, you're free to do so. But you don't have to. I want you to be aware that this is a way to do things. You might have just spent the last 5 minutes copying things down and saying, I don't want to do that. I just want to do it the way I'm comfortable with. Okay, good. That's all you need to do. But this is out there for you. Okay, before I ask for any last questions, I forgot to talk about these at the very beginning. We talk about heat sinks. Here I have an old Pentium 3 processor, which is probably older than many of you. It's attached to a heat sink with thermal paste stuck up against it, so there's conduction between the processor and this piece of aluminum. And then we have machined out this aluminum, so there's a lot of fins. We're trying to increase the area that when convection comes through, which is HA, delta T, there's more A, there's more area. The bigger the area, the more heat transfer, the more heat we can pull away from this processor. The cooler it can be, the better it runs. We don't want to run things over. If we run this, if we put air through this, we would have one type of H. If we were to put water cooling on the top of this, we'd have a different type of H. If we have laminar flow or if we had turbulent flow, we have different types of different heat transfer coefficients. Our goal would be to cool down our processor to the acceptable range. Okay, made of aluminum. Here's one's made of brass. You can see at the back of it has some thermal paste on it. We deal with this stuff all the time. Okay. The other thing that I brought to class, I thought I forgot to tell people about it before. I told you I was going to bring it. This is a koozie I talked to you about in the lecture. This koozie is I bought this, one of my first things I ever bought here as a student, as a faculty member. It says, technology brought to you by your K-State engineers. I have conveniently took away the name of the organization that gave me this koozie, because on the back of it, it says an endothermic beverage capsule. Okay, what is an exothermic reaction? It gives off heat. What is an endothermic reaction? One that brings in heat. I don't want a koozie that brings in heat. Okay, I think they used the wrong word here. I know they used the wrong word here. The word they were looking for was adiabatic. Okay, so I bought this. I think I spent like $5 or $10 on this. I bought it and said, burn the rest of your koozies in an exothermic reaction. And I didn't see it for like 5 years. And then I went to the Manhattan Discovery Center, and that organization was there, and they said, we have some old swag we want to sell. And they were selling these things. And I made a scene at the Manhattan Discovery Center. I said, please get rid of these. I don't know if they did or not, but if you see these, I'm giving you permission to steal them and bring them to me, okay? Law enforcement will understand. You're doing the work for thermodynamics. They will be completely fine. They probably will arrest you, but I will bail you out, okay? Anyway, Any questions about today's lecture, about what we talked about today? This is the only time, this is the only lecture that we're going to be calculating these Q dots. The rest of the time we're going to be solving for these equations. We're going to be manipulating the equations to solve for them. We're not going to be directly solving for a Q dot. But there will likely be a question about heat transfer on your exam. You need to know the area, surface areas. You need to know which equation to bring in. You need to know how to read the problem and know what information needs to be plugged in so you can chug out. Okay? It should be easy points, but areas usually cause problems, and negotiating what words are provided, like what is heat transfer coefficient and what is thermal conductivity, sometimes that causes some issues. All right, we've got our 45 minutes up. Until next time, we'll see you.